Welcome students for General Principles and Processes of Isolation of Elements, Part 4th. In this video, we shall be studying about Ellingham diagram and refining of metals. In Ellingham diagram, we shall be studying about thermodynamics involved, which helps us to understand students spontaneity of a given reaction. Various terms involved are delta H, which denotes change in enthalpy, delta S for change in entropy, followed by delta G, which is change in Gibbs free energy. Thus student, we can have an equation, that is delta G is equal to delta H minus T into delta S, wherein T stands for absolute temperature. Always delta G value should be negative for the spontaneity of the reaction. Now let us understand Ellingham diagram. It is the plot of standard free charge change as a function of temperature for the formation of oxides, chloride or sulfides of various elements. Let us understand thermodynamics principle of metallurgy by an example. When metal M solid state is reacted with oxygen vapors, it forms metallic oxide in the solid state. Thus, we can write change in enthalpy, that is delta H, would be negative, whereas change in entropy is also negative, because on the reactant side students, oxygen is present as the gaseous state, whereas on the product side we are having metallic oxide which is present as solid state. So change in entropy decreases, that is the value is negative. Therefore students, we can use the equation difference of Gibbs free energy is equal to difference of enthalpy change minus temperature into change in entropy. Therefore, from delta H we can write down as negative, whereas minus absolute temperature multiplied by ds, that is change in entropy, which is also negative for the above equation. Thus student, at a higher temperature always change in Gibbs free energy is positive, whereas at lower temperature change in Gibbs free energy, it is negative. Now let us consider second equation, that is oxidation of the carbon. When carbon is made to react with oxygen, the formation of carbon monoxide occurs, and in this case student, change in enthalpy, it is negative, because it is an exothermic reaction, followed by change in entropy. Now on the reactant side student, oxygen we are considering 1 mole of a gas, whereas on the product side we are obtaining 2 moles of carbon monoxide. Thus entropy increases, thus delta S, that is change in entropy, is positive. And students, using the equation change in Gibbs free energy is equal to change in enthalpy minus absolute temperature into change in entropy. So this would be resulting in as the value of change in enthalpy is negative, student, followed by minus T, and ds value is positive, that is change in entropy is the positive value. Thus we can conclude that at a higher temperature, change in Gibbs free energy would decrease. Thus student, delta G value decreases with increase in temperature for the given equation. Now let us consider one more reaction for the carbon. That is, when carbon is oxidized, we obtain carbon dioxide molecule. In this case student, once again change in enthalpy, that is BH, is equal to negative, followed by change in entropy. Oxygen molecule on the reactant side, it is 1 mole of a gas, whereas on the product side student, again the gaseous state, that is carbon dioxide molecule, which is also of 1 mole. As a result, change in the entropy on both the side, reactant as well as product side, both are the same, that is 1 mole. As a result, change in entropy becomes 0. Thus, once again we can use the same equation, that is change in Gibbs free energy is equal to change in enthalpy minus T into change in entropy. Thus student, change in enthalpy value is a negative minus the absolute temperature multiplied by change in entropy, which is 0. Thus, in such a case, delta G is independent of temperature for the given reaction. Now students, let us consider in general for the reduction reaction of metallic oxide. When metallic oxide represented as MO, where M stands for the metal, is reduced by combining with the carbon to form metal plus carbon monoxide. So metallic oxide is getting reduced to metal, whereas the reducing agent, that is carbon, is getting oxidized to carbon monoxide. In this case student, metallic oxide is stable, then reaction will not happen. If the metallic oxide in the given equation is a stable one, then this reaction will never happen. Whereas student, if the carbon monoxide is a stable molecule, then the reaction will happen. Now students, let us consider Ellingham diagram. In this, we are plotting temperature in Kelvin scale versus delta G naught, that is change in Gibbs standard free energy in terms of kilojoule per mole. The first graph represents oxidation of carbon to carbon monoxide, which is a descending slope, whereas oxidation of carbon to carbon dioxide molecule, it is horizontal to or parallel to the x-axis. And the next, oxidation of carbon monoxide to carbon dioxide molecule, it steadily increases, whereas student, in case of magnesium getting oxidized to magnesium oxide, there is increase in the curve, whereas at a particular temperature it sharp rises. Oxidation of aluminium to aluminium oxide also steadily increases, whereas oxidation of zinc to zinc oxide, a very sharp rise within the curve can be observed, whereas oxidation of iron to ferrous oxide, it is a steady increase in the curve. The oxidation of mercury to mercuric oxide, also sharp increase. Oxidation of silver to silver oxide, steady rise in the curve can be observed, With this, students, we can now study about some of the features of Ellingham diagram. The first point, the graph for the formation of a metal oxide is a straight line with a upward slope. Second point, there is a sudden change in the slope for some of the metallic oxides. For example, student, magnesium oxide, which you can observe, followed by zinc oxide. There is a sudden change in its slope, and the next one is the mercuric oxide. Moving to the next point, for few metallic oxides of mercury and silver, the graph is at the upper part within the Ellingham diagram. For both silver and mercury, student, metallic oxides of them, they are placed in the upper half of the Ellingham diagram. And the fourth point, the graph for the formation of carbon monoxide is a straight line with a negative slope. Fifth, the graph for the formation of carbon dioxide is straight line parallel to the temperature axis, that is x-axis. Now students, let us consider some of the significance of Ellingham diagram. In this, the first point, the positive slope of metallic oxides shows that stability decreases with increase in temperature. Thus students, the decrease in their stability is because of an increase in delta G naught value associated with metallic oxides. Second, the sudden change in the graph shows a phase change, that is in magnesium oxide, zinc oxide and mercuric oxide, student, there exists a sudden change which signifies that a phase change either from solid to liquid or liquid to vapor phase. And the third one, the negative slope of carbon monoxide shows that it becomes more stable with increase in temperature. And the fourth significance is tendency of the metals to undergo oxidation, and that is in the order, students, magnesium followed by aluminium, zinc, iron, mercury and silver. Silver being less reactive because it is a noble metal. And this order has been given because due to the increase in the negative value of delta G naught for the formation of metallic oxides, which goes in the order magnesium oxide with the higher value, followed by aluminium oxide, next zinc oxide, ferrous oxide and lastly silver oxide. Now students, let us consider importance of Ellingham diagram. Both silver oxide and mercuric oxide can be easily decomposed at a temperature of 600 Kelvin and 700 Kelvin. Aluminium oxide, students, can react with magnesium metal forming magnesium oxide and aluminium metal. This explains that magnesium is more reactive compared to aluminium. Thus, it displaces the aluminium from its metallic oxide. Now, let us consider reduction of ferric oxide with a carbon at a temperature of 900 Kelvin to form iron along with carbon dioxide molecule. Similarly, when zinc oxide is reduced at a high temperature of 1500 Kelvin, the formation of zinc along with carbon monoxide occurs. Now let us understand formation of carbon dioxide and carbon monoxide molecule from the Ellingham diagram. both the slopes are intersecting at a particular point. From the same point, we can draw a perpendicular towards the x-axis, and the perpendicular line bisects the x-axis of the temperature at 1000 Kelvin. And from the Ellingham diagram, students, it is clear that for the formation of carbon monoxide 900 Kelvin is required, and for the formation of carbon monoxide it requires 1500 Kelvin. Thus, students, at lower temperature, carbon monoxide acts as a good reducing agent. From the earlier discussions, it is very clear that ores can be reduced by the carbon only if its delta G0 value is below that of one of the carbon oxidation reaction. That is, student, lead oxide, cupric oxide and silver oxide can be reduced by using the reducing agent as carbon monoxide, whereas if ferrous oxide has to be reduced, then we can use the carbon. In the metallurgical process, after extraction of metal from their concentrated ore, it has to be refined for the purification of metal. Now let us understand definition of refining of a given metal. Purification of the crude metal by removing both metallic and non-metallic impurities is known as refining of a metal. Students, refining of metals consists of 7 different methods, and the first one is the distillation, followed by liquefaction method, and the third one electrolytic refining, fourth pooling method, fifth zone refining, sixth vapor phase refining, and seventh it is chromatography. One by one, each of the refining process we can study. So the first one as the distillation in detail. In distillation, this method is used to remove the non-volatile impurities from volatile impurities. And students, you need to know about non-volatile impurities. Non-volatile impurities are the impurities which are having higher boiling point, whereas the volatile metals, these are having lower melting and the boiling point. For example, zinc, cadmium and mercury metals can be purified by using distillation method. Let us study the principle involved in the distillation by the diagram. In this case, students, we are having the very important part, that is distillation column. Let us consider principle involved in the distillation process, student, by considering the distillation column. In this, impure metal is heated in a retort and the pure metal easily vaporizes because they are highly volatile, followed by condensation of the metallic vapors would be giving us the pure metal, whereas the non-volatile impurity, students, it would be left behind in the furnace. This diagram represents one of the distillation column which is used to distill off the volatile metals. Now let us consider second refining method, that is liquefaction. Liquefaction method is employed when impurities are having higher melting point than the required metal, whereas the required metal are having lower melting point. Let us understand the principle involved in the liquefaction. The low melting metals forms a fusible liquid on heating and flows down. For example, students, metals like bismuth, tin, lead and mercury are separated from their crude form by means of liquefaction method. Now let us understand working of liquefaction method. Impure metal which is added at the top of sloping earth and from the bottom it is constantly heated. Impure metal runs down the sloping earth, but only the pure metal would be converted into molten state and it can be collected at the lower end of the sloping earth by a receiver as a pure molten metal, whereas all the impurities are left behind in the sloping earth. In this way, student, we can very easily separate the impurities from the pure metal, as our pure metal are having lower melting point in comparison with the impurities which are having higher melting point. Let's continue with the third refining method. It is electrolytic refining. Let us consider principle involved in electrolytic refining of metals. Impure metals are refined in an electrolytic bath containing aqueous solution of their salts. So it is called as electrolytic solution. Always the impure metal would be made as anode, whereas the pure metal would be made as cathode. For example, copper gets dissociated to form cupric ions with a liberation of 2 electrons at the anode, whereas cupric ions get reduced at the cathode rod. As a result, we can get pure metal, that is about 99.99% of the pure copper at the cathode rod by means of reduction. The next diagram represents an electrolytic cell which can be used for refining process. And the fourth method of refining of metals is pooling. In pooling method, which is generally employed in the purification of copper or tin, which mainly contains the oxide as the impurities. Let us understand this by a diagram. Impure metal is placed in a container, students, and by using a green log of wood, it is continuously stirred. As a result, we get molten metal along the ends of the container, whereas a scum is also formed right at the top of the mixture. Now, let us understand the principle involved in the pooling method. The hydrocarbon gaseous component would be liberated by green log of wood, which reduces the metallic oxide into metal. Thank you, students. In the next video, we shall be studying about refining methods and extraction of zinc metal. Thank you.